Alright, so this is the review session for electric circuits for the AP Physics exam. So current is the movement of charge. It goes in the direction of the positive charge. So since we always look at current as the flow of electrons, which are negative, we say that conventional current goes against the flow of electrons. In a circuit, it would be directed from the positive terminal of the battery to the negative one. Its unit is a coulomb per second, which is known as an ampere. The current I is equal to the charge Q over the time t. So here you have a wire or some sort of straight conductor, and you have sort of cross-sectional area kind of thing here. Hey, you've got a bunch of charges kind of going generally in this direction. Yeah, there's a bunch of charges, and basically we've got resistance, right? So essentially the resistance would depend on the length of the resistor and the cross-sectional area. The unit is the ohm, and resistance is the opposition of current. So here we have Ohm's law. It is stated by V equals IR. Okay. This means that the potential difference is equal to the current times the resistance. So this would be the potential difference over the resistor that's in question. So then you have current density, and that is the electric current per unit area of the conductor's cross-sectional area. It is denoted by J, and its unit is amperes per meter squared, and it's got J equals I over A. So the current density can be related to electric field by this equation. J equals the conductivity times the E field. In this equation, we have that the resistance of something is equal to the resistivity constant, which depends on the material and would be given to you, times the length of the resistor over the cross-sectional area. So now we have power in circuits. It's measured in watts, and the equation we commonly used is P equals IV. So using Ohm's law, we can obviously quickly derive these two equations. So if a problem is related to power of batteries, it is talking about the power supplied to the circuit by the battery. If it's talking about resistors, it's talking about the power dissipated by that resistor as heat. So now let's look at resistors and circuits. Here's a series circuit. Basically, a series circuit is something that has a common equal current going through a loop. So the total resistance in the circuit would simply be the resistors added up, the resistances of each resistor added up. And to find, for example, the uniform current, you would take the V divided by the total R, which is this, and then you would get I. So for a parallel circuit, it's a different story. You've got 1 over R total equals 1 over R1 plus the rest of them similarly. So it's also important to remember that here voltage would drop proportionally to the ratio of this resistor to the total resistance. So that's pretty intuitive. But here the potential difference across each of these is the same. And another thing that's different about parallel is that the current going through each of these branches is different, and to solve for the current, you would also use proportions of the resistors. So an ammeter is a device used to measure current, and you would put it in series, and it would ideally have zero resistance. A voltmeter would be connected in parallel, like this, and ideally it would have infinite resistance. This all makes sense because an ammeter, if it was to be in series, you would want to have a minimal effect on the circuit, and here you wouldn't want some of the current to go into here, like it's another parallel branch. So you would want as much resistance here as possible. A capacitor consists of two parallel plates that are conducting, and an insulator between them, or an empty space. The insulator between them would be called a dielectric, which always raises the capacitance. So, if you have some sort of initial capacitance, and you insert a dielectric later, you would take that dielectric constant, which is different from the other K that you know, and you would simply multiply them, and you would get the new capacitance of the capacitor. So, capacitance is how well a capacitor can store charge. Its unit is the farad, and it is equal to the amount of charge in that capacitor over the potential difference over that capacitor. So for parallel plate capacitors, you could use this equation, and it is equal to epsilon naught, which is this constant over here. This doesn't really matter, you don't need it that much. And it is multiplied by the area of one of the plates, which are both the same, divided by the distance between the plates. There's a couple of equations for energy of capacitors, which are QV over 2 or CV squared over 2. So in series, capacitors behave like parallel resistors do. So 1 over CT equals 1 over C1 plus, and so on. In parallel, they behave like normal resistors, like series resistors. So we'd have CT equals C1 plus C2 plus C3. Did I do that? I don't think I did. Okay. So sometimes you might have problems with battery with internal resistance. It's not really much, it's just like you've got the EMF and a resistor inside the battery, and like the actual voltage of the battery would equal the EMF minus the voltage drop across that resistance depending on the circuit. So now you've got Kirchhoff's rules. So you have the loop rule, which states that the sum of the changes in potential around a closed loop in the circuit, for example this one, would be equal to 0. So here we have 0 equal to V plus the current going through here, which is I2, times the resistance R1, and then if we go here, we have I5 R4, and if we go here, we have I7 R5. So this one would be positive, since that's what we start off with, and since everywhere else it's a voltage drop, these would be negative. So that would be equal to 0, that's an example of the loop rule. Then you have the junction rule. And it states that the currents entering a junction would equal the currents exiting the junction. So I1 is going here, and it's going through this junction. I2 is separating, and I3 is separating. So I1 is equal to I2 plus I3. That's the junction rule. Capacitors and resistors will be used in combination in circuits. So you know that the voltage across the resistor would be IR, and the voltage across the capacitor would be Q over C. So you can equate the EMF of the battery to that, to the sum of these two voltages. We know that I is the change in Q over change in time, so we plug that in here. We solve for the differential equation, and then we integrate. So we know that after some time t, this capacitor is going to reach a charge of Q, so we sum up from 0 and 0 to Q and T, and we get these two equations for charging a capacitor. This would be the Q as time increases, and this would be the potential difference of the capacitor as time increases. So this is the graph for charging, and as you can see, there is an RC over here, which is commonly known as tau, which is basically a T thing. And at time t, we know that the amount of charge reaches 63% of its maximum charge. The maximum charge is CV, so this one would be 0.63 times CV. So it's essentially, theoretically, it approaches this, though in practice it basically reaches it. And this would be the discharge graph. So here's an example problem. It is problem 1989 E3. The first part is asking you to find the energy stored in the capacitor when it is fully charged. When the capacitor is fully charged, you can use this equation, and then all you do is just plug in the voltage and the capacitance, and you solve. Then, part B asks to determine the work that must be done in increasing the space by adding a dielectric into the capacitor. So, we know that capacitance is inversely proportional to the distance between the plates. So, since it is 4 times as much, the new capacitance becomes a fourth of the original. But since we have this equation, we know that it would be, the new voltage would be 4 times the original voltage. So, we take since we know work is equal to energy, we take the new energy and subtract it by the old one, and then we solve, and you should get 3600 microjoules. So part C is asking you to determine the current in the resistor immediately after the spacing is increased. So you can calculate the new voltage. Since we know it's 4 times the original, it's 4 times 20, which is 80. And then we simply use Ohm's law, and we plug in the difference, which is the voltage of the battery minus the voltage over the capacitor. So the original one was 20, and the new voltage of the capacitor is 80, since this is the one that was increased by the dielectric. So we find the difference between those two, and we divide that by resistance, and you should get 2 times 10 to the negative 4th amperes. Alright, so part D is asking to determine the total charge that is passed through the battery. So here we know that Q equals CV, that's the general charge equation. So we solve that for the initial charge, which the capacitor would have started out with. So here we have Q initial, which is the charge of the capacitor when it had its original spacing. And here is the one where the spacing was changed. So we know that the difference between these two amounts of charge should be how much charge left the capacitor. So you take the difference and you get 90 microcoulombs. So that should be the amount that is passed through the battery. Part E is asking you to determine the energy that has been added to the battery. So we know that energy, the change in energy would be the change in charge times the voltage. So we simply take our old value, 90 microcoulombs, multiply it by the original 20 volts, and we get 1800 microjoules.